So in today's lecture, we are going to discuss a very important problem in data mining. This problem refers to the dimensionality reduction when building data mining or pattern classification or just machine learning problems in general. But first of all, we need to discuss what a dimension is. So we can say that in data mining or just in pattern classification, machine learning, it doesn't matter. A dimension refers to either a problem or an attribute or a feature describing the problem we are modeling. Okay? Here it is important to mention that we have features and we have instances. So the instances are the observations. uh are the observations, while the features are the variables describing the observations. Okay? So in the case of this traditional pattern classification problem, so we have four features describing the problem, and we have a very special attribute or feature called the decision class. So in this particular example, the decision class is the attribute play, and it has two values only, no and yes. So it means that this classification problem is binary, right? And here we can say that we have four features, but actually the ID feature is not relevant when building a data mining model. And the reason is because data mining is about finding patterns. And of course, if we have an ID feature, we cannot use that feature to discover any pattern, because basically the values are changing all the time. So by definition, there is no pattern in that feature. Another remark is that in the literature, only the features describing the problem are often recognized as such. So it means that the special feature called decision class is often called that decision class, while the variables of the problem describing the problem are the ones referred to as features. Okay, but this is just a taxonomy in the literature. Okay, let's take now the well-known iris flower dataset in order to illustrate how those features look like. So here in the iris dataset, we have three types of flowers. So we have iris setosa, iris versicolor, and iris virginica. Okay, excellent. So those are the values for the decision class. So they are the decision class values. Okay. However, each type of flower is described by four attributes. So here we have the petal and we have the sepal, and in those flowers, and therefore we use the petal length and the sepal length in order to describe the flower. Okay, so we have three decision classes and we have four attributes, okay, describing the flowers. Of course, this is just a toy example to introduce the lecture and the relevance of plotting and understanding how those features relate with each other and the distribution of those features and so on, because this lecture is actually is concerned about problems which are actually described by more dimensions. Because if we have a data mining model and this model is built on a particular on a data set and we have only four features, this is something that is feasible. So we don't need to be concerned about that problem. However, the problem comes when we are trying to build data mining models uh, using data described by, I don't know, thousands of variables or hundreds of variables. Okay? Now, in order to understand how important are the features in order to build the data mining or pattern classification or machine learning model, let's analyze the well-known problem of distinguish a cat from a dog. So this is a classification problem which is very common in the deep learning and machine learning fields. Now, if we are trying to build a classification model such that we receive an animal and the model should be able to produce a decision class, whether the animal is a dog or a cat, this is something that, of course, we need features because we need to describe the animal in order to provide those features to the model. Okay, because in the end, the model is built on those features, right? Okay, if we use only one feature, the model will be very likely to put all animals together within the same class or just make wrong assumptions. So it means that we cannot distinguish properly a cat from a dog by using only one feature. However, if we include two features, for example, the length of the whiskers and the type of ear, describing the ears, for example, you can see here in this example that we can build a model, which is this linear model here, separating quite well the cats from dogs. For example, in this cluster here, we have 3 cats and 1 dog. So this model is not able to properly separate cats from dogs, I mean perfectly. And here you can see another model that is able to associate those 3 cats here and here and here, while the dogs here are in different regions. Of course, this is something that we don't have, right? This is the ideal scenario, and we should be able to build a model in order to do so. But again, using two features, that is not possible because you can see here that with a line, we obtain this partition. However, this is how the function should look like, okay? In order to properly separate perfectly, let's say, separate cats from dogs. However, when using three features, we can build a hyperplane, and that mathematical function, which is the classification model, should be able to indeed separate cats from dog perfectly with only three features in this particular example here. So the final message here is that we need the proper number of features to describe the problem if we want to obtain nice classification rates, which translates actually into a model with high predictive capabilities. So my point here is that if we are more feature dimensions to the problem, each instance becomes more unique. So we can actually separate better the classes. However, at the same time, we are increasing the risk of doing overfitting. And if you remember well, overfitting is the phenomenon in which we approximate very well the training data. However, we fail when generalizing. I mean, when receiving new data, which is the test data, the performance is not the same as the one we computed during the training the training phase. Okay, so this difference between the training error and the test error is just a very strong indicator of overfitting, and this is something that we are going to observe if we increase the number of dimensions without any control. Okay, so the main message here is that having a few features is dangerous because we cannot describe properly the problem, but at the same time, having too many dimensions, it will be a problem because we are increasing the risk of doing overfitting as well. So we need to find the trade-off. Well, the thing is that in order to prevent that, we need to find the trade-off I was talking to between the number of features described in the problem and the number of instances. Unfortunately, the number of instances we need to include in the data sets when adding a new dimension to the problem actually grows exponentially, and this is of course a problem. Okay, because even if we have access to the data we need to in order to create the enlarged, let's say, data set, we are just increasing the complexity of the problem, and we need more time, and we need to build a model, which, by the way, is going to be expensive, computationally speaking. Okay, so that was the discussion dedicated to the feature selection. I mean the dimensionality reduction, and why we need feature selection, feature extraction, and those strategies we are going to discuss in the next slides. But first, let's talk a bit about visualization. Let's assume that we have a number of features, and those features are manageable in the sense that they are just small. Therefore, we can build proper visualization models, or just visualize the data in order to get insights from the data we have and the problem we are trying to solve. So why visualization is so important in data mining? So the main reason is because we have several methods, and we should be able to adjust our expectations when building the model, but at the same time we should be able to select the model that fits best the data we have. And the way we have to do so is by exploring the data and visualizing the data we have. Okay. Okay, one of those strategies is actually the box plots. This is something that we were discussing during the practical sessions. And the box plot is the way we have to visualize a numerical variable. So it provides information about the minimum, the maximum value, the median as well, and also the outliers. So the outliers are quite important because this is a way we have to detect extreme observations. Okay. Another strategy concerns with the histograms. So basically, this is the way we have to plot the distribution of a numerical value, the variable. So we can understand how the data behave, okay, in a more qualitative way, okay. For example, if we know that a variable has a Gaussian distribution, this is a feature or a piece of information we can use in order to select the proper model. Another way to explore the data is by using scatter plots. This is something that we were also discussing in the previous lectures and also in the practical sessions. And this is a way to contrast the performance between two numerical variables. Sorry. And at the same time, we can build combined charts like this one, which includes both the scatter plot and also the histogram in the main diagonal. So it's quite informative. Okay. But of course, if we want to explore the data, the only way we have to do that if we have a few number of dimensions. If we have, I don't know, 100 dimensions or thousands of dimensions, it will be really difficult to explore the data, if not impossible. Therefore, we need dimensionality reduction. But actually, this is a motivation for sure, but this is the trivial one, because not everything concerns with the visualization of the data. Another thing is that the algorithms we want to run, the models we want to build, they are quite sensitive to the dimensions. So it implies that we are going to need more time to build the model if the number of dimensions is too much, basically. But at the same time, we were discussing how sensitive some algorithms can be if the number of dimensions are is just too much. Okay, and the discussion relates with the overfitting problem. So, in summary, we should be able to select or just reduce the attributes we have, the features we have, in order to find a proper trade-off between between the representation of the problem, because we want to represent well the problem, and minimizing the risk of doing overfitting. So this is the issue we want to prevent here. So in order to reduce the dimensions, we can use several approaches. The first one is the feature selection approach. The second one is the feature extraction, and the third one concerns with hybrid approaches. So in the case of feature selection, the idea here is that we want to select a subset of features that actually describes the problem properly. In the case of feature extraction, we want to describe the problem as well with fewer dimensions. However, in order to do so, we are going to build new features from the original ones. So this is the main difference between feature selection and feature extraction. And in the case of the hybrid approaches, we can combine the original features with other features which are created during the feature extraction process. Okay. So now we are going to discuss the feature selection approaches. And we have here three main approaches that belongs to the feature selection. The first one is the filtering strategy. So basically, the problem narrows down to finding which features can be discharged. This is something that is the main concern. And in order to do so, we can assume two different strategies. The first one is that we treat each feature independently, or we treat the features as they belong to a subset of features. Okay. In both cases, the important characteristic here is that the results don't depend on the model. So we don't have any particular model. So in this diagram here, you can see that we receive the training data, which is basically the complete data set, and we have the filter method. And this filter method is composed of two pieces. The first one is the search strategy, and the second one is the objective function. Well, the search strategy is useful when you want to produce different subsets of attributes or features. Okay? If you want to treat each feature independently, then the search strategy is not needed. Okay? And in the case of the objective function, this is a measure, this is a criterion we can use in order to assess the quality of a particular feature or a subset of features. Okay. Some measures we can use are, for example, the correlation coefficients, the consistency coefficients, the mutual information, the significance tests, and also measures based on the entropy, such as the information gain, which, by the way, is one of the criteria used in the construction of decision trees. Okay. And finally, the result of this process is the selected subset of features, which are the ones, the features we are going to use in order to build the classifier. So the second strategy concerns with the wrapper one. So instead of using a measure or an objective function, um, we are going to use a classifier. So basically the classifier, so this classifier here, the inner classifier, let's say, is the one in charge of producing the evaluations for each subset of attributes or just an independent attribute, okay? And of course, this is the evaluation of the classifier is something that is going to be as the information who is going to flow back to the search strategy. So this here is an information loop between the search strategy and also the evaluations produced by the inner classifier. And at the end, we want to produce a subset of features, the ones we are going to use to build the final classifier or the regression model. So here it can be more flexible, okay? Of course, this strategy often produces better results. And the drawback here is that the whole model depends on the classifier. So the features we are going to select are the ones that the classifier, the inner classifier, feels comfortable with those features, okay? But if we change a classifier, there is a risk that we can actually end up with a different subset of features, okay? And therefore we say that this wrapper strategy is dependent on the classifier selection. And there is another final strategy within the feature selection approach, and this strategy concerns with the embedded one. So here the idea is that we are combining the wrapper strategy with the filtering strategy, okay? For example, in the case of the lasso regression model, so when computing the weights, we are basically performing a wrapping strategy because we have a model, which is the regression model itself. But at the same time, the lasso regression model includes a regularization component, which is this penalization here, that actually tries to produce values or weights which are close to zero. So we can focus only on the important weights. The remaining ones, they are going to be discharged. And therefore, this is the filtering strategy. By the way, this is the regularization idea of deep learning models as well, the L1 regularization. Okay. This strategy is possibly faster when compared with the wrapper strategy because the classifier is just the model. Let's say the model is just adjusted itself, so we don't need a different uh, model or a different classifier in order to distinguish which features are important and which are not. Okay. So everything is integrated into the same model, and therefore it will be very likely more fast. Okay, so this strategy is integrated into the learning strategy of this last regression, for example. Okay. Now we have another approach. We have the feature extraction, which is quite important, and we are going to discuss why. So in the case of feature selection, we assume that we can find a subset of features which are good enough in order to build the data mining model, the perfect data mining model we want to. But what if we cannot find those features? What if those features independently, they are not strong enough in order to produce the perfect data mining model we want to? So in that case, one way to go is by using feature extraction algorithms. And probably the most important representative of those algorithms is the principal component analysis, or just PCA. So the idea here is that we want to extract features. So it means that we want to build new features based on the original ones. Now, in the case of the PCA, the features have some characteristics. Okay, the first one, for example, is that the original features can be recombined into the new ones. Please notice that there is a typo here. So it should be new ones because we can build more than one feature. So those are a type of artificial features because they are not the original ones, but a combination of the original ones. Okay. The second characteristic here is that the new features are linear combinations of the original ones. Because of course we can combine or recombine the original features in different ways. But in the case of the PCA algorithm, this is something that we are going to do by using linear combinations. Okay. And another characteristic is that the features we produce, they are not correlated. So we can be more or less sure that the data is described by independent features. Okay, this is important. Finally, the new features, which are called principal components, are weighted by their relevance. So we can know to what extent those components are different from each other and the amount of information they represent. Okay, like for example, here you can see that the first dimension, which is the principal component, includes 73% of the whole variance, while the second dimension, which is the second component, includes the almost 23% of the variance in the data sets. Okay. Now, when it comes to the PCA, we need to understand how this algorithm works. So here in this slide, I included some math in order to explain my point here. So you don't need to be concerned about the details of the math, but the idea behind the PCA algorithm. For example, let's suppose that we want to obtain the first component. So the first component is just the feature, the extracted feature that maximizes the variance in the first axis. And the way we have to do so is by solving this optimization algorithm. So basically, we want to find a weight vector satisfying this mathematical expression. The only restriction here is that the norm, the Euclidean norm of that vector must be equal to 1. Okay? So someone says, perhaps it was a professor I had when I was a bachelor student, that everything in artificial intelligence can be solved as a search problem. And PCA is just an example of that statement. So it's an optimization problem, and therefore it leads to a search problem. And hopefully, in the case of PCA, we know the solution of that optimization problem. And the solution is deterministic. So it means that we know the analytical solution of that optimization problem. And this is how the solution looks like. Okay? So if we want to obtain more components, we just need to subtract the different instances we have from the components we already have. And that's it. Later on, we are going to obtain different instances which result from the subtraction operation, and we repeat the same process. So basically, we want to obtain the weights and the components, maximizing the variance in the data sets. So those components actually explain properly the data. Okay. And here, this is how the algorithm looks like. So we start with the data containing all instances and the whole set of features. And later on, we rotate the first axis just by solving the optimization problem in the previous slide. So when you are actually solving that problem, the thing you are doing, geometrically speaking, is you are rotating the axis. Later on, after the rotation, we just lock that dimension and you proceed with the following dimension and so on. So every time you perform a loop, you discover a new feature, which is a principal component. So we have the first principal component, the second principal component, the third one, and so on. Okay? So when it comes to feature extraction, some people say that the main difference, or at least one of the differences between traditional machine learning and deep learning, is the role of feature extraction. So I realize that this is a bold claim. However, let's elaborate a bit. So in machine learning, like or data mining like this course, we need to perform the feature extraction ourselves. So it means that we need to properly select the algorithm in order to produce the features, the recombination of different original features, which are the extracted features. And later on, we build the classification model or the regression model using those extracted features. However, in the case of deep learning, the feature extraction is already included into the model. Like for example, deep learning, deep neural networks. So we can say that the values of the hidden neurons in a deep neural network are the values of the extracted features. So, in short, we can say that the hidden neurons are the extracted features. Of course, it depends on the architecture of the network. For example, in the case of autoencoders, we can see that the number of hidden neurons are decreasing. Okay, so the number of hidden neurons decreases from one layer to another. Okay, and every time we are going down and down and down, so we are compressing more information and we are obtaining the extracted features we want to. The question is, can we visualize those features? Because in the first slides we were discussing about the relevance of the feature visualization to understand the problem we have and how to properly model the solution? Well, it turns out that we can. However, the extent to which we can understand the inner representation of those features, this is something we can discuss. For example, this image you are seeing here, which is a bit strange, is the result of passing the Mona Lisa picture or painting through a deep neural network. And the thing you are seeing there is just the result of the hidden neurons, which are, by the way, the extracted features that the deep neural network uses to perform the classification. So this is something we can see here, and this is something we can visualize, but I'm not so sure whether I'm comfortable with this image. And for sure, this is something that is not so easy to understand. My main point here is that when we are using the feature extraction, we need to be aware that the new features, they can be difficult to interpret. And this is something that we need to bear in mind, because sometimes we need to solve data mining problems and we need to be able to explain the solution to the expert or the user we are working. And if that is the case, then probably the facial extraction is not very convenient, just because they are not natural features. They are artificial features. But okay, this is something that we just need to be aware of.